So Aayush is doing a Bachelor of Science degree in Actuarial Science. What that degree has got to do with the interior of the Earth? Good question, and Aayush will explain all of that. Probably not much, but we like to have students explore different areas. So so his project is supervised by Luke. What's Luke's last name? What he said. And I will now let Aayush.
Good afternoon, everyone. My name is Aayush, and I'm currently heading into third year of Actuarial Science. So the main reason that I was attracted to this project was essentially due to the fact that I was keen to investigate the Earth's inner structures, understand its mechanics. Furthermore, I was really interested in understanding how its implication is to real life, such as like earthquakes and volcanoes. And lastly, I wanted to expand my coding knowledge, how to implement ideas and how they're used in projects that can be implemented in real life. So before I begin, I would like to just give a brief background on the earth science and the stuff of the little things here and there that are essential for this project. Essentially, as we all know, that the Earth is made up of multiple different layers, as Figure 1 shows. It consists of the crust, the mantle, the outer core, the inner core. The composition of these layers itself are vastly vary, and to investigate this, a process is used, which is called seismic tomography. Now, what is tomography? Tomography itself is just using sectioning, which is just cutting it up through any uses of penetrating waves. Now, in earth science specifically, you use seismic waves, and seismic waves are formed through explosions or earthquakes. So essentially what is done is that you just, the data set itself is you just shoot it straight through, and then you can see the seismic velocities. Now, in the general aspect, or the general view behind it, is essentially that all seismic waves should travel at the same speed across the same line if the Earth itself was homogeneous. That is that it is chemically similar. However, we all know that it's quite mysterious, it's complex in nature due to its multiple structures, its thermal variation. So that causes velocity anomalies, essentially where the seismic velocity travels faster or slower depending on the medium itself which is going through. So in general overview, it is that the deeper that you go into below the Earth's surface, the faster the seismic velocity is, and that's basically due to the fact that it gets hotter and hotter. Now, if large low shear velocity provinces, which are LLSVPs, were essentially found and discovered through seismic tomography, what they are essentially is just two colossal blobs sitting on the Earth's mantle. So you can see on the second figure here, you've got the two red images that are just sitting across the Earth's inner mantle. Now, the reason that they're quite important is that they affect a lot of the Earth's properties. They're thought, to affect multiple of the Earth's properties. These include such as like magnetism and especially volcano interaction. This then leads me to mantle plumes, which is the final figure here, which is essentially just hot rock, which is just convected to the top of the surface. As you can see, the red part here on the last figure, that it's convected to the top of the surface, and it's thought to be the cause of volcanic centers. So, in this project itself, there were two main prior models that were discussed. The first one on the left here is the Kotar model. The Kotar model itself was quite, if you can look at it, if you see it, it's quite interactive, it's quite visual, and it shows the LLSVPs. However, it is not descriptive. It lacks those sort of descriptive properties that are needed, that are presented as well in my suggested model. Secondly, the image on the right here is called the submarine model. Essentially, it's just this model itself is just the opposite of the Kotar model. It lacks the visual properties. It's not very pretty. It's not 3D as well, but it is quite in depth. But it gets to the point where it's just too much information, and for starting users, it becomes too not user friendly. So this leads me to my own new and better model, which is shown on the right here. And the main reason that I'm presenting this model is because it has those visual features. Furthermore, you can actually section it up, you can slice it up, you can play around with it, which some of the other models can't. So it just becomes a better and overall model that can be used. So in this project itself, I went through a series of 4 steps. I extracted the data set, which was just a bunch of CSV files. Went through a bit of coordinate system conversion just to plot into a sphere. After that, I visualized that point cloud, which is point clouds are essentially just X, Y, Z coordinates on a 3D space, and voxelated it. Voxelating itself is just making little Lego-like cubes instead of having the points itself. After making that final model, I made the user interface, which allowed the slider widget, the slicing widget, and the checkbox widget just to make it a bit easier and allows for a deeper analysis. And finally, I just polished it up by attaching a color map, texture mapping, and just playing around with the opacity so that becomes better user-friendly. So the first step was the data files. As you can see on the second image here, there are multiple CSV files ranging from 50 kilometers to 2850 below the Earth's surface. They contain 4 columns. They're geodetic coordinate system, it's called the longitude, latitude, the seismic velocity, and the depth. There's a bunch of them, so essentially I just combined them up and made them into one big file. But before I did that, I went through a series of conversions to convert that geodetic coordinate system to Cartesian so that you can actually plot it on the sphere itself. So from there, I converted through the equations, on the first figure, just a bunch of simple equations that are quite actually easy to understand. And it gave me X, Y, Z coordinates. And the A value, which itself was the seismic velocity. If you look at, there's a difference in A value because it goes from negative to positive. That's just to make it easier for us, just to only have positive numbers so it's easier to plot and easier to visualize. So this is the first visualization of the point cloud. As you can see on the outside and the inside when I zoom in, it is color mapped across with the seismic velocity. As you can see as well, it is quite interactive, so you can rotate it, zoom in, zoom out, whatever you want. It was a good starting step. So from there, we went through, I went through a process of voxel modeling. Now, essentially, like I explained before, voxel modeling is just making little Lego-like cubes of it. And the image on the right below the cube, explains the whole process. Essentially, you just have the image and you just convert it into a bunch of cubes. You might be asking, why do we actually need this? Why is it important? And it serves 3 main advantages in visualization. So firstly, it provides more precise modeling, and that's because it allows for, it mimics actual data particles. So that allows for just a better visualization. Secondly, it allows for deeper simulation techniques. All of that stuff is never been done before, and it's really good to just get to deeper visualization. And lastly, it's efficient to use. It's the quickest way to visualize volumetric data sets, which is my own, and just becomes easy to visualize and also allows a better modeling. So this was the actual voxelated point cloud. So you can see some of the outside, you can see some of the actual cubes itself. It's a similar image, but instead of having the points now, sorry, I might have zoomed in too much. It's got the cubes itself now instead of the points. So from there, I then, even though that model, it is quite good, it lacks some properties. So firstly, there's no locations on there, and for someone who's like a beginner, they wouldn't know where to start, they wouldn't know where everything is. So I added the locations of key hotspots. And then from there, I also added in a slider widget, and the slider widget itself is such that it masks any voxels so whatever the user picks, that's the only voxels that are shown. And lastly, I added slicing, just all these features so that when it's used in future research, or if anyone wants to really use it in the future, it becomes quite easier to understand and you can get better contrast and comparisons. So adding the locations itself was quite simple. Firstly, it was just going through a series of steps of just converting the coordinate systems. That was, once again, like I explained before, it was exact same process. It's quite simple to do. And the slider widget here, so firstly you can just see I've attached the locations across it. The slider widget, like I said before, it creates a threshold, and any values above that threshold will not be shown. And so obviously what I've shown below the threshold is visualized. So if you look here, the original image, I've set the seismic velocity, at 7.49, and now I've set it at 9.03. And if you look at the color scheme at the bottom here, 9.03, any values above that will not be displayed on that image. So just by having these user interface constructions, it really helps deeper the analysis, and it can be really useful for a lot further research. So from there, I then made a slicing widget, which you can see is just simply just a box around it, and wherever the user chooses to rotate the box and move that little arrow, that's pointing in, you can just slice the model anywhere you want. You can see the cross sections, so you start to see the actual seismic velocity inside the sphere, and it just becomes, once again, for further research, it is quite important for this to happen. So lastly, after I made that sphere itself, another thing that we thought was important would be having a texture map over it. Texture mapping essentially is just getting any image you want and just wrapping it around. The image that we chose was just a highlighted continents texture map. The reason we chose a continents texture map was just simply due to the fact that now you can start analyzing continents, the continents by continents, and not only that, you've got the locations itself. So from there, you get, instead of just having just the locations, the contents will provide a better analysis. So the way that this was done through Blender, which is just another software. Essentially, it was just making a UV sphere, which is just, if you look at the first image, it's just a sphere with rings and segments in it. There's nothing special about it. All we did was just make it and just made the same radius as the Earth, which is 6,371 kilometers. So then after we made that sphere, we simultaneously plotted them on top of each other so that the texture map is seen on the outside. And you can see that on the final image on the top right here, that you can start to see some of the continents that are coming through. Lastly, that model itself was quite good, but there was some changes that I had to do. So firstly, I tweaked the opacity because if you saw in my previous images, it wasn't see-through, so I decreased the opacity such that you can start to see the inner structures. That's essentially what we really want to see anyway, so we have to, I dropped the opacity by like 0.2 and help me really start to visualize some of the inner structures. And the second thing as well is the color map. Color maps are surprisingly really important. I wasn't actually sure about that, and until Carly explained to me what they have a lot of significant meaning. Essentially, there's 4 types of subclasses. There's a sequential, there's diverging, there's cyclic, and there's qualitative. Qualitatives are for data sets that are random in structure. So you can see that on the bottom here, that the color scheme is just quite all over the place. It matches the random structure. Cyclic itself is just that when you've got endpoints, so normally with some sort of spheres at the top and the end, like the North and South Pole, you'd want those to be colored differently. Diverging is that where you have a medical critical value. Essentially, it's just used for anything that is like a rectangle, is you want to pinpoint something in the middle. And sequential, which is, in my opinion, what I perceive to be with data sets that have structure, And if you look at the second box, from the top, the one that I chose was magma, which is 4th from the bottom. There is no special reason why. I just thought it matched my data set well, and it allowed a diverse range of colors so that you can really perceive and actually really visualize what's going on. So this is my final product. As you can see here, you've got the seismic velocity at the top. That's a slider widget, you can manipulate that as you wish. You've also got the continents texture map across over there and the slicing widget so that you can cut it wherever you need. I've also just put in a simple checkbox widget just so that you can turn on and off the texture map, just because I feel like when you're actually interacting with this sphere itself, it can be a bit harsh sometimes to just get around and understand what's going on when there's a massive texture map across over it. That was my final product. So for future work itself, the actual rendering speed of the model is not super slow. It is slightly slower than I expected it to be. So we discussed through a better visualization experience through ParaView, which is just another software that strictly does visualization. This project, was done through Python, just Python only. So going through ParaView would be a good next step. Furthermore, if I just go back, on here, there's only one slider widget. So you can only control one of the thresholds. It would be good to have multiple of those so you can start really getting in an upper bound, a lower bound, and just like even if you have like 5 sliders that you can play around with, it just becomes a lot. You can start getting a lot better visualization, and not only that, but you can compare and contrast a lot more aspects of the model. And lastly, I would love to see some of these models compared through a time series, essentially just having data sets from 10 years ago, 20 years ago, and seeing how the structures of the are changing throughout time, seeing what's actually going on. That would be a really good next step. Lastly, I'd like to thank Luke Dissett, my primary supervisor, who helped me with the guidance throughout this project, and Carly especially for her expertise in coding. She really assisted me through there, and Kurt and HIVE for providing me with an amazing opportunity and their general support. Thank you so much for listening.